I'll be talking today about connecting CO intensity mapping to essentially high redshift galaxies, and specifically molecular gas and star formation high redshift galaxies. Again, here high redshift is about 2 to 3, but this talk will go in a somewhat different direction than previous talks, but I think it's also quite relevant and potentially quite exciting. And this is work I've been doing with my advisor, Risa Wexler, but also with the Sarah Church's group at Stanford. So let me start briefly with a bit of motivation. This will come as no surprise to anyone here, but in galaxy surveys, there's an intrinsic trade-off between going wide and shallow or narrow and deep. And this is quite fundamental as long as all of our observations are based on collecting photons. But what this means is that at redshifts greater than about 2 or so, it becomes harder and more expensive to observe typical galaxies in complete samples over wide areas. And it's certainly possible to do, and there's certainly been exciting progress made on that front. But this is an ongoing challenge for both cosmology and galaxy formation. It's a challenge for cosmology because you need to trace large-scale structure with high number densities over large areas. It's a challenge for galaxy formation because individual observations of galaxies need to be placed in the broader context of their evolving populations. Right? So intensity mapping is a technique that targets this observational gap in a regime that's inaccessible by traditional galaxy surveys. And so briefly, what intensity mapping is essentially is a technique that focuses on a single spectral feature, in this case a single spectral line, and maps it out across cosmological volumes. Right? And so to do this, there's a bit of a trade-off. You have moderate angular resolution, so you fuzz out your resolution a bit, and you're no longer resolving individual galaxies. Instead, you're aggregating flux from multiple galaxies, and you have high frequency resolution, which gives you line-of-sight structure, so line-of-sight resolution. Right? And in this work, I'll be focusing on the CO10 line. And this is the lowest energy, the transition between the 2 lowest energy levels of this the rotational levels of the CO molecule. And briefly, we've heard this before, but the significance of this is that it simply traces molecular gas, at least in low redshift galaxies, and we hope in high redshift galaxies as well. There is an actual experiment motivating this, and that's the CO mapping array Pathfinder. It's currently being built by a collaboration of Caltech, JPL, Stanford, Maryland, and Miami. But the essential points here are that the Pathfinder is a single-dish experiment, which will be observing in the 30 to 34 gigahertz band. And so that gets you CO from redshifts of about 2.4 to 2.8. And for the purposes of this work, we've also modeled a full, more ambitious experiment that essentially has better sensitivity, finer resolution, and wider area, also observing the same redshifts. Okay. So I can briefly just go through this slide. But CO at redshifts 2 to 3 is particularly interesting here because we're in a regime, a redshift regime, where we're at or near the peak of cosmic star formation. And I think most of us have seen some version of this plot before. But the redshift range is highlighted in this red box here. And you see we certainly have data going all the way back to reionization redshifts. On the right, I've shown a similar plot for the molecular gas history. The thing to note in this plot is that almost everything here is modeled, and there's precious little data here. Right? And so if we can probe CO in this redshift range, then we can probe molecular gas in galaxies in this redshift range, and then probe the fuel for star formation in this redshift range. So the basic questions that are motivating this work here are essentially, A, what do we expect to see? And B, what do we expect to learn? So in other words, for the first part, if we assume a fiducial model that's based on our current knowledge of galaxies, what do we predict the CO intensity mapping signal to be? And more specifically, what do we predict the power spectrum of the signal to be? And the second part is motivated by the large uncertainties in the first part, and essentially asks, if we are given a mock observation, what could we infer about galaxy populations from that mock observation? Right? So to summarize our modeling process, we essentially start with dark matter halos, and through a series of empirical relations, we arrive at star formation rates, infrared luminosities, and CO luminosities, and we add on some scatter at the end. And so each step along the way is constrained by various empirical relations, and then we arrive at mock 3D CO intensity maps and their power spectra. Right. So the mean CO halo relation that we get is this black line here. You can see it's broadly consistent with these colored lines, which are previous studies. One thing to note is it's not linear, which almost seems like a trivial thing to say, but it actually affects the shape of the power spectrum, which I'll show later. But basically, what goes in is on the x-axis, what comes out is on the y-axis. So for a bit more visual intuition, right, this is the volume of halos within our Pathfinder survey volume, right? So you can see each dot here is a halo. We're observing CO from 30 to 34 gigahertz, and that goes from about redshift 2.4 to 2.8. If I take slices in perpendicular directions, you can see just quite clearly the structure, the large-scale structure that's traced out by these halos. Right? When we apply our model and go through the process of creating CO intensity maps, we end up getting these slices here, right? So these are the same slices, but now converted to slices in the CO intensity map. And you can see you no longer resolve individual galaxies, but here's a key point. You still resolve the same large-scale structure. Right? So we want to know, can we use that structure, and can we use the information contained in that structure to make inferences about the underlying galaxies? Okay, so the main statistic, so to speak, here is the power spectrum. And what we've done with the 3D intensity map from before is take the spherically average power spectrum, and this encodes cosmological structure. So you can think of this power spectrum as having a clustering component, so this hump at low k, or large scales, and the shot noise component, which in this plot goes as k cubed, at high k, or small scales. And so the first point to note is that in our fiducial model, the signal appears to be detectable. Right? So given parameters that describe the noise and resolution of the instrument, and therefore the sensitivity and the variance due to that noise, we get a total detection significance of between 7 and 8 sigma for the Pathfinder, and 144 sigma for the full experiment. This is making the strong assumption of uncorrelated errors, but it's certainly an encouraging indication. Okay. But more relevantly here, the power spectrum not only encodes cosmological information in the structure, but it also encodes properties of the galaxy population. Right? So if you change the normalization of the CO halo relation, the normalization of the power spectrum changes. It's probably not altogether surprising. But also if you increase the halo-to-halo scatter, you also get an increase in shot noise, and you essentially wash out your clustering signal because of this large scatter between different halos and their CO luminosities. And the power spectrum is sensitive to this in a measurable way. As well, if you change the weighting of faint galaxies, so if faint galaxies are more CO faint than we expect or less CO faint than we expect, the clustering signal, the relative strength of the clustering signal also changes. Right? Again, in a measurable way. And these colored lines here represent different fits in the literature to the IR-CO relation, but the basic point here is that as you increase the weight of faint galaxies, the clustering signal, this hump at low k, increases. Right? So this motivates the next part, which asks, what could we actually learn from a CO intensity mapping observation? And briefly here, what we do is we put in a mock observation. We run it through an MCMT procedure, which also has priors attached to it, which are informed by existing observations. And we get out parameter posteriors on our CO model. So the first constraint that we obtain from this process, or could obtain from this process, is for the infrared CO relation. This has been shown before, so I'll just skip over this slide. But basically, these colored regions here are 68% credible intervals for the IR-CO relation in this model. Our fiducial model is shown in black, and other fits in the literature are shown in these gray dotted lines. The point here is that the information in this observation is coming directly from the faint galaxies, albeit in aggregate, but it's coming directly from their flux. Right? The second constraint we obtain is for the CO luminosity function, and this is not a direct input into our model. It's actually another statistic that comes out of our model. But our the black line is our fiducial model, and the blue and the red contours are now the 95% credible intervals for the CO luminosity function, right? And you can see that you actually recover the faint end quite well in here. Right? So just for a point of comparison, how does this compare to models or observations that have come before? What I plotted here in the gray band is a Walter et al. 2014 observation that constrained the CO luminosity function at about redshift of 2.75. And the black line, the black dotted line here is an Obreshkov et al. 2009 model. This is this is qualitatively different from our model, but it's just as a point of comparison. You can see that observations get down, getting close to the knee, but it's increasingly difficult to reach this faint end and measure that slope there for the luminosity function. So I'm running out of time, so I will just summarize here. There are three main takeaway points I want to make here. The first is that in our fiducial model, the predicted CO intensity map appears to be detectable at around redshifts of 2.4 to 2.8. The second is the CO-halo relation and the details therein measurably change the power spectrum. So there is information contained in the CO power spectrum. And the third is that intensity mapping could potentially place useful constraints on the underlying galaxy population in a regime that's not accessible currently or difficult to access with galaxy surveys. Right? And so to sum up, we need diverse probes of the high redshift universe. The hope is that this could be one of them, and potentially a powerful one. Thank you.
Well, that's a very impressive theoretical approach to astrophysics problem. Allow me, however, to take a very dim view of the possibility that this will lead to cosmological success. You've already seen, of course, what Linda talked about, how complicated the conversions, so to speak, are in these multi-parameters which we can study.
Absolutely.
And there are many which we haven't studied.
Absolutely.
The most important one is metallicity.
Yes.
And so we know from the local universe that the CO flux to H2 mass ratio is a very strong function of metallicity. We had this with macromoles before the discussion, such that below a metallicity of half, the CO flux dives into the basement. And so the problem is that as you probe the fainter galaxies, which we cannot yet probe, all you're doing now is you're basically, so to speak, you're measuring how fast this breakoff is. What will you learn about cosmology from this? So, since the function is so steep, I see no hope there to get physics out.
So there's two separate questions here. One is getting cosmology out of this, and the second is getting information about galaxy formation out of this. And they're certainly related. But they require different surveys and different strategies. So for cosmology,
you will get information about the cloud structure and, so to speak, how CO is destroyed, not about not about galaxy formation, in my view.
Right. This is certainly not the end-all, be-all of measuring CO in galaxies. This is just one more step towards measuring the molecular gas content of galaxies. But so I think this is relevant to your question. A question you could ask is, what happens if we don't see anything, right? If we in this, in our, so the second part of this procedure, what if we get a non-detection or something that's consistent with a non-detection? And if we run this through the model, we get constraints on the luminosity function here, or at least 95% allowed regions that place essentially limits on the luminosity function. And these are sensitive to your priors. And so this method doesn't work in a vacuum. You need galaxy surveys to constrain the bright end of the luminosity function. But in tandem with intensity mapping, you can still place constraints on the faint end. If you don't see anything, that's also informative, and it may be scientifically interesting. Right? So,
sorry. I have to cut this discussion.
Okay.
We have to move on. Sorry about this.
Certainly happy to chat about it.
Thanks, Tony. Next.
I'll be talking today about connecting CO intensity mapping to essentially high redshift galaxies, and specifically molecular gas and star formation in high redshift galaxies. Again, here, high redshift is about 2 to 3. But this talk will go in a somewhat different direction than previous talks, but I think it's also quite relevant and potentially quite exciting. And this is work I've been doing with my advisor, Risa Wexler, but also with the Sarah Church's group at Stanford. And there's certainly been exciting progress made on that front. But this is an ongoing challenge for both cosmology and galaxy formation. It's a challenge for cosmology because you need to trace large-scale structure with high number densities over large areas. It's a challenge for galaxy formation because individual observations of galaxies need to be placed in the broader context of their evolving populations. Right? So intensity mapping is a technique that targets this observational gap in a regime that's inaccessible by traditional galaxy surveys. And so briefly, what intensity mapping is essentially is a technique that focuses on a single spectral feature, in this case, a single spectral line, and maps it out across cosmological volumes. Right? And so to do this, there's a bit of a trade-off. You have moderate angular resolution, so you fuzz out your resolution a bit, and you're no longer resolving individual galaxies. Instead, you're aggregating flux from. So let me start briefly with a bit of motivation. This will come as no surprise to anyone here, but in galaxy surveys, there's an intrinsic trade-off between going wide and shallow or narrow and deep. And this is quite fundamental as long as all of our observations are based on collecting photons. But what this means is that at redshifts greater than about 2 or so, it becomes harder and more expensive to observe typical galaxies in complete samples over wide areas. And it's certainly possible to multiple galaxies. And you have high frequency resolution, which gives you line of sight structure, so line of sight resolution. Right? And in this work, I'll be focusing on the CO10 line. And this is the lowest energy, the transition between the two lowest energy levels of the the rotational levels of the CO molecule. And briefly, we've heard this before, but the significance of this is that it simply traces molecular gas, at least in low redshift